Right. Class. Okay. So, the last section we were talking about heat engines. And again, there's a lot of different types of heat engines. So the first video, we're just talking about like fundamental physics, like conservation of energy, or the first law of thermodynamics, and then applies to all heat engines. So like anytime there's a difference in temperature, heat wants to flow from hot to cold. And there's a lot of different ways you can take advantage of that heat, that flow of heat. And so we talked about a lot of different types of engines. And the first one, that conservation of energy, that's just universal. That's true for all of those. But now, in this topic, we want to talk about one particular type of engine. Remember, every engine, we have to have a cyclic process so we can keep repeating it over and over and actually get some useful work out of it. And so it's called a Carnot Cycle or Carnot engine. You can kind of use those interchangeably. So what is a Carnot Cycle? Well, the name Kernel, that was named after a scientist named Sadi Carnot. I don't know if I'm pronouncing that name right, but he's the one that came up with this. And we actually want to think of this as kind of like a theoretical engine. So we can imagine building something like this, but we're not actually going to build a Carnot engine. It's not a practical thing. But we'll see later a couple reasons why this Kernel engine is so important. So to start out with, I kind of drew the whole cyclic process here. We'll go over each step. And over here is a PV diagram. So we're going to start at state A, when we're at our lowest volume. So remember, volume is on the horizontal scale. This is the leftmost point. So we're at the lowest volume, say right here. So we have our cylinder. This is the piston. The gas is in this small volume here. And we have some mass on top of the piston just to supply pressure, to compensate for the gas pressure pushing up. So we have gas pressure pushing up. We have this weight of this container pushing down. And it remains, it's balanced. And so what we're going to do, we'll say this mass. Say it's a light container that's filled with like metal balls. So they're fairly heavy, kind of like lead or something. So we have this mass that we can alter if we want. We can take balls out and lower the mass if we want. And that's what we're going to do. So for the first part of the cycle, we're going to go from A to B. So we're going to start out at this small volume. And if we start removing these lead balls, let's do this slowly. And then we're taking weight off. Pressure is still pushing up. It's going to rise up. And remember, when the volume increases, the pressure will decrease. And so, it'll go, the height will depend on how much weight is pushing down. So we just keep removing these and the volume will increase. Now, typically what happens when if you just let a gas expand, it's going to cool off. However, we're in contact with this hot reservoir. And so, as the gas is expanding, if it starts to cool off, heat's going to flow in. And so we imagine we do this process isothermally. We just take these balls out slowly, then it expands slowly. So it's not going to really cool off. Just whenever it starts to cool off, heat will flow in to compensate. So the gas is going to remain at this temperature, TH. And so this from A to B is an isothermal. And just a quick review from the ideal gas law. For an isotherm, T is constant, R is a constant, N is the amount of gas, that's fixed, it's all in the cylinder. And so the entire right side of this equation is constant. So for an isotherm, pressure times volume equals a constant. Okay, so now we're at point B. So we're at this volume B. And now we want to keep expanding to volume C. But what we're doing is we're removing this hot reservoir. So we continue taking mass out of this container, so it's going to continue to rise. But now it's doing so adiabatically because it's not in contact with a reservoir. So there's nowhere for the heat to go. Again, this might be a bit of an idealization because the container itself, heat could flow into the cylinder itself. We're going to say it's very well insulated. So, again, somewhat of an idealization, but say we expand it from B to C adiabatically, just by removing more weight. Now, for an adiabatic curve, I wrote this equation here, PV to the gamma equals a constant. Now, gamma we talked about before, that's that ratio of specific heats. We have specific heat at constant pressure and constant volume, and gamma is that ratio of those two different specific heats. And so it's a number and it's greater than 1. It depends on the particular gas, monatomic, diatomic. Real gases can be more complicated. Something like H2O, water vapor. That's a more complicated molecule. But anyways, gamma is a number that's greater than 1. And so on a PV diagram, if we plot this adiabatic process, it's going to look kind of like an isotherm, except it's going to be steeper, because gamma is always going to be greater than 1 for a gas. Now, you might be asking, where does this equation come from? And for this video, we're just going with this. Now, I might record another video just for those that are interested and try to explain this. It's very difficult to do in an algebra-based class. So I'm going to think about this and see if I can come up with a way to come up with an algebraic way to explain this equation. But for our purposes, we're just going with this. So for an adiabatic process, PV to the gamma is a constant, and then we're going to go from B to C. So again, we're removing weight. There's no more heat for the heat to go. So as it expands, it's cooling off. And that's why we're going down, this new temperature, Tc. Once we reach this maximum expansion, the gas is cooled off to this lower temperature, Tc. And when it's here, we place it in contact with a cold reservoir at that temperature, Tc. And now we're going to start adding more weight. So we start putting these balls back in the container. So we've got more weight pushing down, so that's going to compress the gas. And of course, compressing a gas causes it to heat up. But now that it's in contact with this cold reservoir, that heat that builds up can go into the cold reservoir. So we do this slowly so that the gas remains at this colder temperature, Tc. So again, we have an isotherm going from C to D. So now we're pushing the cylinder back down. Again, we have to get it back to its initial volume so that we can repeat the process. So we're expanding it isothermally from C to D. So on the PV diagram, that's from here to here. And again, we're dumping heat into a cold reservoir to make that happen. So remember, that's an essential part of any heat engine, is you have to dump that heat into a cold reservoir. Otherwise, it doesn't work. Because if we can't we have to cool the gas in order to repeat the cycle. If you don't cool the gas, you could just say let the gas expand and do work, and then you could do work to push it back to its initial state. You can always force it there, but you're going to wind up doing more work than you'd ever get out of the engine. So to make an engine that's going to produce net work, we have to be able to dump heat into this cold reservoir. And then what we do is we remove the cold reservoir, and we just put the rest of the mass back in, kind of slowly, and we let the gas compress until it's back to its initial volume, and now it's doing that adiabatically. And it'll go back to its initial temperature, TH, and so we're back at point A again. On our PV diagram, we've gone through our complete cycle, and we're back where we started. So basically this Carnot cycle, again, you never actually build an engine the way we described here. In theory you could, and that's all that really matters. This Carnot cycle is more theoretical than anything. So as long as it's something that could be done, then we can talk about it. Okay, so I'm going to erase this picture, And then we're going to focus on this PV diagram. So, yeah, I think we have everything we need over there on the board. And I'm going to need a bit of space on the board, I think. So, I'll just erase this board entirely. So, for a Carnot cycle, 2 isotherms, 2 adiabatic processes. So, we're going to start out by looking at an isotherm. And remember the first law of thermodynamics, delta U is Q minus W. And we know that the work done for an isothermal process, and again, basically we want, like, what's the area underneath this line from, say, A to B. And again, finding the area underneath a curve, that's a calculus problem. Sometimes you can get away with doing calculus problems by hiding the calculus and making it just pure algebra. Not in this case. We have a natural logarithm. So, yeah, I've never figured out a way to explain this in an algebra-based class. So, again, another thing, you just have to kind of trust me on this one. Okay. So this is the work done for an isothermal process. Remember, isothermal, let's just say for simplicity, say we have a monatomic gas. It would work just as well with a diatomic gas, but the internal energy, it just depends on the temperature. An isothermal means a constant temperature. And so delta, for an isotherm, delta U equals 0. So, yeah, just on any isotherm, because the internal energy only depends on the temperature. So if there's no change in temperature, there's no change in energy. And so, yeah, delta U is basically just equal to minus W. Now, yeah, so we can put all this together. Now I want to get rid of that minus sign. We're just going to look at, because remember when we talk about engines, we always put the Q's in absolute values. So, yeah, we're going to ignore that minus sign. So, oh, here, delta U is 0. And so Q equals W. So yeah, we don't actually have to ignore that yet. We'll talk about that later. Actually, it's with the adiabatic one. And again, that W is, so let's summarize everything here. So Q is equal to W. So Q is equal to nRT times the natural log of V final over V initial. Okay. Now, yeah, we have to be a little bit careful when we look at, we have 2 isotherms here. So let's look at QH. That's when, heat is, we're expanding the gas, and so heat is flowing in to keep it from cooling off. So QH is going to be positive. And that's going to equal nRT times the natural log of VB over VA. Okay. Now, there's kind of different ways we could look at the next isothermal process from C to D. And it turns out the direction we're going doesn't actually matter. But why don't we look at it the way it's actually going? So we could just put an absolute value sign on it, but let's look at what it's actually doing, because we're going from C to D. However, QC is going to be negative now, because heat is flowing into the reservoir here. We're compressing the gas, and it's isothermal, so heat has to be going into a cold reservoir to keep it from heating up. And so we have to put a minus sign in front. and then we have the natural log of Vd over Vc. However, this is going to be a negative number because Vd is less than Vc, so we're taking the natural logarithm of something that is less than 1. So what I'm going to do, let's look at this. If we have natural log of, say, x to the minus 1, that's minus the natural log of x. So let's move this minus sign over here, just multiply this equation by negative 1, and then we can take this to the negative 1 power. So I'll put that over here, outside of the parentheses. And because that's a fraction to the negative 1 power, we can just flip the indices. So this would be okay. Now, another way we could have done it is just QC. If we just picture it going this way, because the direction we're going on the PV diagram doesn't really matter here. So we have these two results for QH and QC. So QH is, on this temperature, the TH isotherm. Heat is entering the gas, and on QC, it's leaving the gas. Now, I'm going to write these down somewhere. We don't need this anymore. I'm just going to write them down up here in the corner. I'm going to add one thing I should have earlier. Yeah, like this is occurring at a temperature TH. And QC, we're looking at this isotherm. So again, that T is a particular value, TC. Okay, so this was from looking at the two isotherms. And so I'm going to erase this. Let me just double check, make sure. Yeah, that looks good. Okay, so now we're going to look at the adiabatic processes. So for an adiabatic process, we have PV to the gamma is equal, let me just write this down. So here we have PV to the gamma is a constant. Okay. So what I'm going to do is I'm going to write this in a particular way, which is legal algebraically. But, you might at some point be wondering, why would we do this? So there's no question we can, but why did we? So again, first to justify this algebraically, I'm going to think of this as like v to the first power times v to the gamma minus 1. So if you have the same base, you just add the exponents. So we have 1 plus gamma minus 1. That's just v to the gamma. So again, these two statements algebraically are identical. Now why did we do this? Now, PV is equal to nRT. So we can replace this PV here with nRT. So we took this relation, which we're just kind of taking as a given for this class, and we're combining it with the ideal gas law. So yeah, we factored out a PV, or took that part out, then replaced that with nRT. Okay, now again, this relation is true. Like, let's look at a particular adiabatic curve like this. This is an adiabatic curve. And so this relation is true for every point on that curve. So in particular, it's true at point B. So let's look at this first curve here that connects points B and C. We have NR, and at point B we're at a temperature TH, and then we're at a volume VB to the gamma minus 1. So that's looking at point B. And then at point C, we're at the same constant, so we can say that's NR. Now we're at a temperature TC, and this would be volume C to the gamma minus 1. Okay. And again, this is the basic equation that applies to every point on these adiabatic curves. So we just looked at 2 points on the same adiabatic curve, so these two values at these points have to be equal to each other. So this is looking at points B and C. And again, they're on the same adiabatic curve. So this has to have the same value. They're both equal to that same constant, so they're equal to each other. So now let's look at points A and D. Okay, so let's look at point A. We have NR. At point A, we're at a temperature TH. And then volume A to the gamma minus 1. And point D is on the same adiabatic curve, so we have NR. Again, we're at a temperature TC and a volume D. So we've got that equation. Okay. So I'm going to keep these equations and get rid of everything else. So I'm going to erase the board. And basically, we're going to have 4 equations. We're going to have these two from looking at the isothermal processes, and we have these 2 equations from looking at the adiabatic processes. So I'm going to erase everything we don't need. I'll just write this stuff over here. So NRTH VB, the gamma minus 1, NRTC VC to the gamma minus 1. And again, these actually are different things. This is temperature TC, this stands for cold. This is point C on the PV diagram. But then we have NRTH VA to the gamma minus 1 is equal to NRTC VD to the gamma minus 1. So let's put boxes around these. Okay. So now what we want to do is combine all of these things. What I'm going to do is I'm going to start out by looking at QH over QC. Let's do that. So this would be, yeah, let's do this. So we have NR, just to save some space on the board, we're basically just dividing these equations. It's obvious that these NRs are going to cancel out. So let's just say this is TH times natural log of VB over VA over TC times the natural log of VC over VD. Okay. Now again, we're doing a lot of work here. And try not to be intimidated by this. I don't think any individual step is too complicated. So hopefully you can follow the steps. And right now you might be confused, like why we're doing this, yeah, point is we're going to get to a very important result at the end. And the result is going to be very simple to state and remember. It's something on the equation sheet. And to really see the full advantage of a Carnot cycle, that's going to be a different video entirely. So this, we're just going through this process, kind of a difficult process, but hopefully you can follow it. And no, you're not going to have to do this stuff on your own. Like, you wouldn't have this on a test where you just have to, do this on your own. But, following it is much easier. Okay, so now we're going to look at these two equations. Let's divide them, let's just straight out divide them. So again, if we divide this, the left sides, the NR and TH are going to cancel out. So what we have is VB to the gamma minus 1 over VA to the gamma minus 1. And on the right, we divide these by each other. The NRTC, they cancel out. So we just have VC to the gamma minus 1 over VD to the gamma minus 1. Now remember, just in general, let's say you have x divided by y to the nth power. That's equal to x to the n over y to the n. Just algebra. And basically, we're going to go this way. So here we have something to this exponent divided by something else to that same exponent. So here we have VB. We can write the left side as VB over VA to the gamma minus 1. And the right side is VC over VD to the gamma minus 1. So what does this mean? Well, that means that these ratios of these volumes must be the same. Because, you have something, they're both raised to the same exponent and they're equal to each other. Now, again, that doesn't automatically follow that these things are the same as each other. Algebraically, it doesn't. You could have, say, x squared equals y squared. Does that mean x equals y? No, x could be 2 and y could be negative 2. But here, our volumes... Sorry, the phone's making noise. Here, our volumes are always positive. So, yeah, this does follow. Algebraically, there could be an issue. But because everything here is a positive value, then this is going to be true. And this is a very important result, mainly because here we have the natural logarithm of VBA over, natural log of VB over VA. And here we have natural log of VC over VD. But again, VB over VA is equal to VC over VD. So what that means is that these logarithms cancel out. And so this is kind of the final result that we are going for. I guess there's room on the board. So for a Carnot cycle, I'm going to write it, I'm going to look at the way it's written in the equation sheet. Just, you can write it different ways, but finding it. Weird. Oh, okay. Oh. The way I wrote it in the equation sheet, now we have to put absolute value signs everywhere. We're just looking at these magnitudes of heat, and temperatures are in an absolute scale. So they definitely, these are going to be positive numbers. So again, like the way we looked at this, QH is going into the gas, QC is leaving the gas. So like QH is a positive number, QC is a negative number. That would make this equation meaningless. So we were setting it up so we're kind of just looking at the QH and QC as like positive values. So, yeah, this is the way I wrote it in the equation sheet. You can also write it this way. Where the ratio of these heats is equal to the ratio of the absolute temperatures. Again, it's the same thing, just written a little bit differently, algebraically. Again, this is the way I wrote it in the equation sheet, so we'll have that ours. This is kind of like the whole goal of this lecture, was just getting this result. For a Carnot cycle, this relation is true. Now, one thing that's really nice about a Kernel engine, let me erase all of this. I'll just leave the final result. I'll write it in the form that it's in, like in the equation sheet. So yeah, this was kind of, we did all that work just to get this result. Okay, but it's a very important result. So let's look at a normal, let's just say we have a Carnot engine. When it's an engine, it obeys the same rules we had before, where we have a hot reservoir and a cold reservoir. And we have QH. We're taking QH from the hot reservoir. We're outputting work. And we're dumping QC into the cold reservoir. Now, we define the efficiency of an engine. Think about, like, what do we want to get out of the engine? We want to get work out of it. And what we're putting into the engine is QH. So we want to get that. We define the efficiency to be that ratio. Like what we get out of the engine compared to what we put into the engine. And also, just from conservation of energy, what goes in the engine has to come out. So we have this result as well, which I'll write up here. QH equals QC plus W. So we can combine that here as well. We can write the efficiency. Let's get rid of W. Let's say W is QH minus QC. And then the whole thing over QH. So again, this is another way of writing the efficiency of any engine. Now the problem is, it's like, well, what's wrong with that? We just plug in QH and QC. How do you know what those things are? It's hard to tell, like, how much heat's going into an engine, how much is being dumped into a cold reservoir. I'm going to do one more step. I'm going to write this algebraically. We can look at this as QH over QH, which is 1, and then minus QC over QH. So again, this is true for heat engines in general. Okay. Now, what's nice, one thing that's nice about a Carnot engine, we can say the efficiency, let's just say EC, for the efficiency of a Carnot engine. That's 1 minus QC over QH, but QC over QH is TC over TH. So again, the efficiency of a Carnot engine only depends on the temperatures of the hot and cold reservoirs. And that's something that's typically easy to calculate. It's not hard to know what the temperatures of the reservoirs are, but knowing what QH and QC are, like for a real engine, that could be a fairly difficult problem. So at least one nice thing about a Carnot engine is that it allows us to calculate the efficiency very easily. And I'm going to leave it at that right now. We are going to talk more about Carnot engines. But kind of a review of what we've done so far. We started by talking about the 0th law of thermodynamics. And then the first law, And then things like engines and the different types of processes, PV diagrams. But I want to get to the second law of thermodynamics next. So that'll be a separate video. And after we talk about the second law of thermodynamics, we're going to come back to these Carnot cycles. And we'll discover something else important about them. So that'll be it for this one. This was just a lot of work to get through. But what you need to know are basically these two things. The ratio of like QH over TH equals QC over TC, and the efficiency of a Carnot engine. Really, this is all you need to know, because this is just the efficiency of any engine where you plug this into it. So really, this is our entire lecture basically comes down to just this. We want to understand what a Carnot cycle is. It just operates between isotherms and adiabatic curves, and this is the ultimate result. Okay, so this will be a good place to stop then, but we will come back to Carnot cycles.